Hello everyone, welcome to today's presentation. My name is Matt, I'm a structural engineer at S16 Software in Vancouver, British Columbia. And I'll be leading the presentation today, but I'm also joined by a few colleagues of mine who will help answer questions along the way. And today we're going to be talking about steel design using the new CSA S16-19 Annex O.2 process, which will be available soon in S-Steel. Now we don't have enough time to go into much detail on this topic within this presentation, but I wanted to give you a bit of a high-level overview of what we'll be talking about today. Now, first and foremost, this is a newly defined method outlined by the CSA for its use in design of steel structures for its increased accuracy. And it's a method that's meant to capture the effects of residual stresses and initial out-of-plumbness of frames by reducing stiffness and application of notional loads during a second-order analysis. And going a little bit further into this, the notional loads that are used to account for out-of-plumbness are reduced from 0.005 in previous codes to 0.002, which is leading to smaller lateral forces. It also has the ability to automate the application of lateral forces in the most destabilizing direction, which reduces the number of load combinations you would need to define within S-frame. And this helps you capture the critical demand forces without having to create 4 different load combinations per frame. S-frame will also report the ratio of the second order drifts to the first order drifts for each story, and that helps you better understand the stability effects of your model, and will also automatically add or remove notional load contributions when gravity load combinations meet certain code criteria. And this approach is used instead of a first order analysis or an effective length method. And one of the advantages of this is that it relegates the task associated with residual stresses and effective length factors to the finite element solver. So it reduces the amount of work that's required by you to assign effective length factors and whatnot to your model. So in this presentation, we're going to give you a very brief background into this new approach described by the CSA S16 code. We're then going to discuss second order analysis and how you can set up your model for success within this approach. It's very fundamental to the process outlined in Annex O.2 that you use second order analysis, and S-frame can really help you with that. And we'll go through a design example. Actually, we'll go through 2 examples here where we can look at the results from the new code and compare it to the previous code. At the end of the presentation, I'll wrap things up with a few summarizing points and open up the floor for you all to ask questions. So why don't we first go into a bit of background on what this new process that's described in Appendix O.2 actually is. I've done my best to summarize it in one slide here, and as we go through the presentation, we'll start to see some of these different topics in action. So essentially, with this CISC S16-19 Appendix O.2, is changing the handling of the assessment of overall system structural stability, including the effects of geometrical imperfections and reduction of stiffness due to yielding, and is doing this all explicitly within a second order analysis. So we use notional loads that are used to represent the residual stresses in the members, as well as out-of-plumbness. And in the Appendix O.2, it uses notional load factor of 0.2% or 0.002. And these notional loads are actually added or removed automatically by S-Steel, S-frame, in the destabilizing direction based off of the code-defined sway tolerance of 1.7. One of the advantages of this approach is it doesn't require you to calculate effective length factors and apply those to your members. And for some of the models that we see from our clients, this can certainly be a large time saver. It's also applicable to all structures, making it very well-rounded in terms of its use. And again, as I already mentioned, it accounts for things like uncertainty in material strength and stiffness reduction due to inelasticity, and residual stresses and out-of-plumbness. Now, to really wrap your head around this process, it's important that you understand second-order analysis and how you can set up your model for success in this approach. Now, for a bit of background on second-order analysis, basically second-order effects occur in your model, and these can be calculated automatically within SRAM. And these second-order effects will increase the calculated moments, the deflections, and the forces that you would normally experience from a regular first-order analysis or linear static analysis. And there are two methods for accounting for these types of effects. We could do so with a second-order analysis, a p-delta or nonlinear analysis, for example. Or there's also an approximate method using first-order analysis calculations and results from the analysis and applying magnification factors. We'll be looking at option 1 here. So let's just describe p-delta analysis a little bit more and p-delta effects. Let's just imagine a scenario where you have a beam, or maybe a column for that example, and you have a tip load applied to it, an eccentric load, a lateral load applied to the tip of a column. We'll use that as an example. And that induces a deflection, which we're going to call delta. We also have on this column an axial load, so a compressive load, that we're going to say is called F. And with that deflection of delta, our load F, which is an axial load going straight down, is now eccentric to the base. And due to this, the deflections in the members of the model will then induce secondary moments as the end of the member that's holding up that load, F, is now no longer vertical and perfectly plumb with the base. So it's inducing those extra moments due to that additional lever arm that we have between the base and F, which we describe as delta. Then the model is going to be resolved with the new stiffness matrix, and the secondary effects are then accounted for accurately using a p-delta analysis. And this is really important to this whole process. The analysis software that you use must be able to account for both big and little p-delta effects, which we'll talk about. And luckily for you, SRAM does have this capability. So again, here's another illustration of the big p-delta effect, as we call it. I've actually reversed some of these descriptions here of the letters I'm using. So just imagine we have a column that's fixed at the base. The free end here is characterized with this square, and we have a lateral load called F. And we still have this axial load coming from above that is called P. Well, obviously that lateral load F is going to induce some deflection, which we're calling delta, and P, which is still going straight down, is occurring at the tip of our column, which is now eccentric to the base. So we have this moment arm being calculated, or being taking into account now. So how this process works is, first of all, the structure is loaded, as we see on the far left side, and analyzed using a linear static analysis. The structure deflects, and the stiffness of the structure will then be updated based off the stress state and the deflection that we see. A second linear static analysis is then performed on the model with that updated stiffness. And as I mentioned already, this illustrates the big p-delta effects, but we also have the phenomena known as little p-delta effects, which SRAM can also account for. So here we've got the little p-delta effect, and very similar to what we saw before. We've got a situation where we've got an axial load, in this case F, that's being applied to a beam, and this beam is simply supported. We've got pins on both ends, and we're applying a moment on one end, and that moment is inducing some deflection. That deflection here is little delta, and obviously when we have this deflection and this large axial load, we're inducing some additional moments and deflections that wouldn't occur if we were just examining this under a linear analysis. So it can be thought of that comparing to big p-delta analysis or big p-delta effects, which are more of a structural change, p-delta or little p-delta effects are a local deformation of a specific member. And you may want to consider these if you have very large deflections in your model, or perhaps you have very slender columns, which would make them more susceptible to this type of behavior. And this can be accounted for not only in a p-delta analysis, but also a nonlinear analysis if you wanted to consider these little p-delta effects. The one thing you have to keep in mind is that in order to consider this, you have to have more than one analysis element, or really more specifically, you have to have more than one node within your member. And it only requires a single analysis. And the beauty of doing this within SRAM is that you can use physical members. You can have a single physical member with multiple nodes along its length that will make sure that it captures these little p-delta effects. Now in SRAM, unlike a nonlinear analysis, which some of you may be familiar with, where we have the ability to update the geometry for every single load increment that occurs in the analysis, the p-delta analysis will only perform this geometry update for one iteration. So you can think of a p-delta analysis as a single increment, single iteration nonlinear analysis. But you could also run a nonlinear analysis if you wanted to, and that will account for both big and little p-delta analysis effects. Now, why do we require this, and why is it important? Well, the AISC actually provides some benchmark problems for us to validate the p-delta results. And it will help us determine whether an analysis procedure meets the requirements of a rigorous second-order analysis adequate for use within the direct analysis method. Now, obviously, this is a different method, but the AISC provides good guidelines for this that we're going to show in today's presentation. So the first case that they have is case number 1 here, where we have basically a little p-delta effect scenario occurring. We have a column that is pinned on the bottom and has a roller on top with an axial load of p and a lateral load between the spans, and it's 28 feet in length. And a secondary case, which is to consider and validate the large p-delta effects, is another column where we have a fixed base column that's free on the top, but this time we have P again at the top and a 1 kip load laterally at the very top as well. The same length applies, and in this case here we're also using the same material and section properties. So I'm going to go into SRAM now, and I'll show you the first example for case number 1, which again was a simply supported problem that we had. It's worth mentioning that this model here is made up of just one single member, and I can verify that by turning on the member IDs. So this is member 1 here, if you can see that. Or I can even shrink the member from its element ends. You can see that it's shrinking from the 2 ends. Even though we have nodes along the length, it's using a physical member approach, so we can actually have a single member representing this span. If I look at the support conditions, we can see here that we have supports at the top and the bottom, where at the top we're allowing for some translation in the vertical direction, but at the bottom we essentially have a pin connection. I've also simplified this model to prevent any out of plane motion, so I'm going to prevent any Y translation movement at all these joints. We've also applied a material or a section property representative of the one in that example, a W14 by 48 section. And the material that we're using is a steel material. Now, one thing you may notice here, if I look at the model, you can see that I actually have these 3 joints within the span of my column. And those are the additional analysis nodes that I was referring to when I was describing those slides. Basically, they help us represent the type of buckling that we might experience, or the type of little p-delta effects that we might experience when we have a little p-delta situation where we have both ends essentially laterally restrained, but the top end can still move vertically. We need those additional nodes in the interior to really describe that behavior. Now I'm going to go to the loads window, and I can see here that we have 2 load cases. I have an axial load case of 150 kips at the top of the column. And again, I'm using kips because this example came to us from the AISC. And we have a lateral load case of 0.2 kips per foot and that's being applied in the x direction. And this is all being combined into one load combination. Actually, sorry, I have multiple load combinations, but the same behavior in general. So we have one that just contains our lateral loads, one that contains the axial loads plus the lateral loads, one that contains the an increased amount of axial load plus lateral load, and so on. You get the idea. So we're just gradually increasing the amount of axial load we have while maintaining the same lateral load in each scenario. So as we could imagine, the more axial load we put on the model, the more compressive stress it's going to be under, and the more prone to buckling it will be under as well. So we'll be able to observe the behavior of the model under these types of effects. So I'm going to go ahead and I'm going to run a P-delta static analysis. Actually, before I do that, I'll run a linear static analysis just to kind of illustrate something for you. I'll run a linear static analysis. Here we can get a clean solution. There are no diagnostic messages in the analysis, which is what we like to see, ideally. And I'm just going to look at the results for my load combination number 2, which has the combination of the axial load and lateral loads. And again, this is a linear static analysis. So you can see here, we are getting some deflections within the beam, or the column. And if I look at the deflection values here, I can see that I'm getting about 0.2 millimeters as a maximum displacement. And in terms of moments, I'm getting about 235 kips inch. And I think I had the unit wrong. I'm getting 0.2 inches rather than 0.2 millimeters. So that's using a linear static analysis, which doesn't consider the P-delta effects that I'm expecting to exist in this model. Now I'm going to go ahead and run a P-delta analysis, a P-delta static analysis rather. And I'll click OK to run the analysis. And if we investigate the solution trail that comes out of this analysis, we can see here that what happened first was SRAM ran a linear static analysis for all of our load cases and combinations. And what it's doing is it's determining the stress state of the model due to these loadings. And it's running a second linear static analysis on that updated stress model. So that's what the P-delta static analysis is doing. All in one run here, we're able to account for these effects. And now if I look at the results for this load combination, this is load combination number 2 again. Here I can see that I'm getting a slightly higher deflection, 0.23 inches versus 0.201, I believe it was before. And for my moments, again, I'm 235 kips inch compared to 269 or 270. So there is definitely an increase due to the inclusion of these P-delta effects. And keep in mind that the linear static analysis doesn't account for that. But what happens if we increase this even further? So we want to look at maybe the next load combination where we've doubled the axial load that's being applied. Now you can see here that with a higher axial load, we're getting more and more moments within this beam, 315 kip inches now, and 2.69 inches of displacement. And just bumping this up even more, so we have now 3 times our axial load with our original lateral load as well. So we're not increasing the lateral load, we're just increasing the axial load. Every time we increase the axial load, it's getting closer and closer to its critical buckling limit, which is actually causing it to experience more deflections in the lateral direction. It's becoming less stable. And here we can see that we have 0.323 inches of displacement and 380 kip inches of moment. Now I've tried to summarize this all within a PowerPoint slide here. So again, for our case number 1, which is using a simply supported beam, or column I guess we're saying in this case, we have all these different loading scenarios, and we're looking at basically changing our axial load. I forgot to show you the original one, but it's actually consistent with our linear static analysis. That's okay. But basically we're looking at situations where we just have the lateral load, then we don't have any axial loads. That's the 0 kip scenario. Then we have 150 kips for our axial load plus the lateral loads. Then 300 kips, we're doubling the axial load. And then 450 kips, we're tripling the original axial load. And you can see here that we actually have results from the theory. This is calculations done by the AIC, and we're comparing our results to that. So we can see here between the theory and S-frame, there is very little difference for this validation problem. It maxes out at around 0.5% for the deflection at midspan in one of the examples. Now let's look at the other scenario. Oh, sorry, I went a little bit too farther. So let's pretend we didn't see those results. And let's look at the other scenario where we have a cantilever problem. And without going into too much detail, because most of the parameters are the same, the sections, the materials, and everything are the same. One thing that does change here is that this is a fixed base column rather than a simply supported column, or beam, I guess you could call it. And under the loads, I can see that I do have my axial load again and a lateral load case. So my axial load is 100 kips at the tip of the column, and my lateral load is 1 kip to start this off. And just like before, if we go to the load combinations, here we can look at the loading scenarios. So we start off with just the scenario where we just have our lateral loads and no other loads, no axial loads or anything like that. Then we look at the influence of our lateral loads plus our axial loads. Then we increase the magnitude of our axial loads while maintaining the same lateral load scenario. So I'm going to go ahead and I'm going to run a P delta static analysis. Click OK. The analysis runs fine. Again, we already understand now how this works. And we're able to view some of the results. So I'll start off with the first load combination with just the axial load. And I'm really interested in here, I'll turn off the display of our loads, the tip deflection of 0.907 inches and the moment. So we're getting about 336 kip inches. Now we'll move up to the next loading scenario where we consider axial load in addition to the moment. And we can see what effect that has. So it's increased our moment quite significantly. And we're getting about 0.4 inches more deflection when we include the effects of that axial load, because it is stressing that column, putting it under compression, but we're also having that moment arm developing due to the lateral displacement. Moving it one step up, we get even more deflection, and not surprisingly, even more moments. And then finally at the top end here with double our original axial load, we have 857 kip inches and 2.6 inches of displacement at the top. So there's a very large gap between the tip of the column, its original location, and its deflected location, but that axial load is still coming down at that offset location. So it's inducing those additional moments and whatnot. And now to compare this to the theoretical calculations from the AIC, you can see here that once again the results are very close to one another. So we're excited to see very close agreement between the theoretical calculations for the validation model from AIC and S-frame's P-delta analysis results. So at this point, we can go into a design example now that we have a bit of a background in terms of what this CISC S16-19 Appendix O.2 represents and how the second order analysis affects our results and affects our model's behavior, but also can help us get a more accurate analysis result. So we're going to look at a calculation example now. And this example is going to have a 3-bay frame, and the frame itself is 4.5 meters tall, and you can see the varying dimensions of each bay in this frame. And the columns are all represented with regular beam element types that have section properties, a W360 by 196 section assigned. But the beam itself is actually simplified into a rigid diaphragm. So we're basically constraining the tops of the columns to act as a rigid set, so it's going to not be able to deflect inwards into where the beam is. We have leaning columns on the edges. You can see here from the support conditions, the edges are pinned, and in the interior, we have fixed base columns. So those will be our lateral force resisting systems here, these two interior columns. And as we'll see later on, we have 2,000 kilonewtons of axial load distributed on the columns. We're also going to apply a lateral load, as well as a notional load that we have in our load combination. And for the Appendix O.2, we're using a notional load factor of 0.002. So let's just take a look at that lateral load that we have. So we're applying a lateral load of 66.7 kilonewtons just on the top of one of the columns. And because this is a rigid diaphragm at the top, it will distribute those to the other elements. And you can see the distribution of the axial loads as well on top of our columns. So obviously we're trying to, with these loads, we would expect some sort of P delta effect to occur. And keep in mind as well that we are applying a notional load to that load combination where we're combining the lateral and axial loads. We're applying a notional load of 0.002. So again, what that means is that if we tally up all of these axial loads, which equals 2,000 kilonewtons, we'd multiply that by 0.002, and that would be contributing to the lateral loading. So here's my model here. It's actually modeled in 3D space, but for the sake of simplicity, I'm just using a 2D view to investigate it. And I'll start off by looking at our support reactions, and here you can see that we actually have pin columns on the two sides, and then the fully fixed supports on the interior. Not really that much to see with our section properties. We have our W360 by 196 section. Now if I go to the settings menu, and under the preferences option here, the preferences dialog opens up, and I can see under design codes, I have the ability to select the S16-19 code. And underneath that, we also have this little disclaimer, and it says use Annex O.2 for stability effects and elastic analysis. And we have the ability to apply or not apply the 0.8 plus tau b, which will affect the axial and flexural stiffness. It will reduce it when we're running a P delta analysis. So we want to make sure that that apply option is turned on. And if we look at the material properties, you can actually see here that I've applied two different materials. I've created my own material. So I have material 15 is my own custom material, and I'll go into that in just a second. But material number 1 is my steel material. And why don't I actually just drill down into details a little bit more. So if I just open up my material properties, we can see that material number 1 is just my regular steel material. Nothing's too exciting there. But this steel material that I copied, we actually have a new setting made, and this setting is enabled when we have the S16-19 code selected in the settings preferences dialog. You can see here that it says Annex O.2 stability effects and elastic analysis. Applies only for P delta analysis. And it just says this material would be assigned to a lateral force resisting member. Everything else is the same. It's just we have this one flag set for this particular material. And that's material number 15. And if I close this, I can see that material 15 properties have been assigned to my two pin or fully fixed columns, my lateral force resisting system. And then I'm going to go to the loads window and just investigate the loads here. So I actually have all my loads under one load case. So here I've got my axial loads, which again tally up to be 2,000 kilonewtons. And if I look at the lateral direction here, I have 66.7 kilonewtons in the x direction. And just to confirm as well, these are all combined into a load combination with the intention here that we're adding this notional x factor. So we have a notional x factor and just the that load case added with the combination factor of 1. So I'm going to go ahead and run an analysis. I'm going to run an analysis using a P delta static analysis, which we've already discussed at length today, for both load cases and combinations. I'll click OK to analyze. And if I just drag this over to my other screen here, we can see here that it's going through the usual steps of a p-delta analysis, but we have this little note further down. And it's telling me that the lateral loads exceed my notional loads for a situation where B2 is greater than 1.7, or less than 1.7, sorry. And we'll get into that in just a second. But first of all, I want to look at some of the results. So let's take a look first of all at our reaction loads. And I'm just going to actually switch to the head-on view here. And what I'm interested in seeing here is with my load combination result, when I'm looking at the reaction loads, we can see clearly that we have 2,000 kilonewtons of shear Z reaction. And we know that we have 66.7 kilonewtons of applied lateral loads, but we also have that notional load factor that's been applied as well. But if we look at the shear X value in our reaction forces, it equals 66.7 kilonewtons. So that's 66.7, that equals our lateral loads, and it doesn't appear that our notional loads are actually being added in this case, despite the fact that we've entered that 0.002 notional load factor. Well, what happened was that the solver was able to identify that this is a non-gravity load combination, and because of the fact that the lateral loads exceed our notional loads, it's just going to apply the lateral loads themselves. And that's one of the processes described in Appendix O.2. We can look at some of the other results here. So we can look at our deflections, 11.2 millimeters. We can look at our shear forces. Make sure we get the correct orientation, about 34 kilonewton. And our moments, 161 kilonewton meters. So we kind of get an idea for the results within this particular frame. Now let's jump back into our PowerPoint slides now. And just detail some of the results. So again, we had a situation where our frame was loaded with a lateral load of 66.7 kilonewtons. And our calculated notional load, if we go with the Z reaction, remember that was 2,000 kilonewtons, multiply that by 0.002 or 0.2%, we get a notional load of 4 kilonewtons. However, we're only using the lateral load in this situation, so that's what's going to be applied to our model for this analysis using the S16-19 code. So that's why we get our X reaction matching the value of our lateral loads and not the lateral loads plus our notional loads. And we're getting a displacement of 11.2 millimeters. And just to repeat what we saw there, so the solver is just going to use the lateral loads during the analysis. And because B2 was less than or equal to 1.7, the notional loads can then be ignored for the non-gravity load combinations. And in this situation, this was a non-gravity load combination. Now it's also worth mentioning here that the B2 value for this example is less than or equal to 1.7. And for those of you that aren't familiar, this B2 value is basically the ratio between the second order displacement and the first order displacement. Now in the situation where that's not the case, let's say that we have a B2 greater than 1.7, the solver would then actually add both the notional and the lateral loads in that scenario. So we'll treat it differently depending on this B2 value, which is calculated by the solver. And this is also a 2D example, and that was done for simplicity's sake. And it doesn't have to be that way. This could also be in 3D, and in fact, the 2D example doesn't necessarily do everything justice. In 3D, the solver would actually automatically reorientate the loads in the direction that has the most destabilizing effects in the X and the Y. So whether the positive or the negative direction. And for this reason, there's no need to define 4 load combinations. Only 2 are going to be required. Namely, you'd have one load combination with notional loads in the X and another with notional loads in the Y. You don't need to create 2, one with positive notional loads and one with negative. The solver will do all that for you. So it can be a big time saver when you have lots of load combinations. Now let's look at that same model, but let's compare the results between the S16-19 code and the S16-14 code. Again, we're going to use the same model using the same applied loads that we had as well. And I have 2 different models that we'll look at. I'll start with the S16-19 code since we already have that one open. So we're already familiar with some of the results. We're getting 161 kilonewton meters of moment being applied, 11.2 millimeters displacement, and 34 kilonewtons of shear forces. Now if I go into S-steel, I can go ahead and run a code check, and just to verify, if we go to Options, Design Codes, the design code that's selected is the S16-19 code. And I'm just going to go ahead and click Code Check. Remember, with this approach, we don't actually need to apply any effective length factors or anything like that to account for the design lengths. And I'm just going to use load combination number 1. I'll click OK. And you can see that we're getting the same result across the board. So I'm just going to drill down into one of these members and investigate a little bit closer. If I go to Code Details, here you can see that the governing code check is actually the slenderness ratio, which makes sense, I guess, that they're governing across the board. We have the same utilization across the board because they all have the same length. We haven't applied any effective length factors or anything like that. So we have this one governing 0.235. And then we can look at some of the other results as well. So I can see my strong axis shear is using a shear force of 34 kilonewtons. It's nowhere near failing, which is fine. This is just an example, but we get the idea. And our bending stability check, we're getting 161 kilonewton meters. So let's just keep that in the back of our mind. And we're going to go to a different model where we use the exact same geometry and everything, but what we're changing is we don't have the S16-19 code being used anymore. So I'm just going to switch to a different model since I have it all set up already. And just to confirm here, if I go to the Settings Preferences window, under Design Code, I'm just now using the S16-14 code. And keep in mind here, now that we switched back to that old code, we don't have the ability to apply those material stiffness modifiers that we had available to us in the S16-19 option. In addition to that, if I look at the material properties, well, I'm just using the same material across the board because, again, under the material properties tool, I don't have that flag that allows me to designate a specific material as a lateral force resisting material. So that's why, again, I'm just going to use the steel material number 1 across the board. The only other change that we have in this example here is if we go to the loads window, under the edit menu, all the loads that are applied are the same, but the load combinations will be different. So I'm using a load combination factor of 0.005 in the X direction. So it's a higher load combination factor for the S16-14 code. Now I'm going to go ahead and run the analysis. So I'll click Analyze, run a P delta static analysis again. And we'll look at the results. Here I can see that, again, it's going through the same process that we're used to, but we don't get that additional note telling us whether or not the lateral loads or the notional loads are exceeding one another, because that didn't exist in the S16-14 code. And now I'm going to look at the same results here. So I'm just going to look at the reaction loads first of all. And I can see here that we're getting the same shear Z reaction, but the shear X reaction is different. And the reason it's different is that we're taking into account the fact that we have our 66.7 kilonewton lateral load being applied, but we also have our notional load, which again was 0.005. So 0.005 times 2000, that's 10 kilonewtons. So it totals up to be 76.7 kilonewtons. Now if I look at the other results, like if I want to look at the shear diagrams, for example, I can see that I'm getting a higher shear force, 39 kilonewtons. And moments, here I'm getting my maximum moment of 182.7 kilonewton meters, which is also higher. But when I look at the deflection tool, I can see that the deflection is actually lower than what I had before. It was 11.2 before, now it's 10.2. And why is that different? Well, there's a lot of factors at play, but one of the things that we don't do in this approach is we don't apply that material reduction factor, the 0.8 plus tau b, I believe it's called. And if we go into S-steel, I'm just going to code check this. Again, just to verify here that we're using the correct design code. We can see that we have the S16-14 code selected. I'll just run a quick code check for load combination number 1. And lo and behold, we're actually getting the same utilization ratios. So on the surface, it doesn't really look like anything is different. Why would we use a new approach if it's giving us the same results? Well, if I look at the code details, again, I just want to stress that for this particular example, the slenderness ratio is what's governing, and that approach hasn't changed between the two codes. But it's the governing code check, so that's the one that's going to show up first. It's going to SDL will report the governing code check. But when we look at the strong axis shear check, for example, we're getting a higher value. We had 39 kilonewtons for this example in the S16-14 code, whereas before we had 34 kilonewtons. And our bending stability check, we have 183 kilonewton meters, whereas before we had 161 kilonewton meters. So this is changing the demands on our structure in different ways depending on the situation. So just to recap, here we have the two codes compared for the exact same model, with the only difference being the notional factor that's being used. Our shear forces that are being applied are different. We can see here that despite having a lower shear force, the S16-19 code is giving me higher displacements because we've reduced that material property, the stiffness reduction is taking into account, although our shear and moments are lower in the S16-19 example. Whereas in the other example, using S16-14 code, we have lower displacement but higher shears and moments. And again, just to repeat ourselves, why is the shear X different? Well, remember the S16-19 code ignores notional loads in this situation because in this situation, B2 is less than or equal to 1.7, and it's a non-gravity load combination. And the S16-14 code here doesn't use the stiffness reduction that we were talking about earlier to account for the effects of residual stresses and initial out of plumbness and so on. So we are getting some different results between the two. So we can see here the interplay between the magnitudes of the notional loads, the reduced member stiffness, and the P-delta effects differ to the extent that the responses of the structures could be actually a little bit different. And this is just one example. We may find other examples will give us different scenarios that might play out. It's hard to really cover all of these scenarios in a short webinar, but hopefully you'll be able to understand from this process how it works. So today we talked about steel design using the CSA S16-19 Appendix O.2 process that's been described. We went into a little bit of details on the background, again just scratching the surface because there's a lot that we can cover here, but we just don't have the time today. We then looked into second order analysis, how that can help us really capture the true behavior of our model and set us up for success with the steel design process. And then we went through a few design examples as well. Now I just have a few summarizing points to make, and then I'll open up the floor for you guys to ask any questions. So through this process, hopefully you're able to see that it does simplify the steel design process. There's no need for effective length factors. It also helps when defining load combinations. You don't need as many load combinations in the negative and positive directions. It will streamline that process for you. And the software will actually take care of that all as well. In addition, this process is accounting for things like initial imperfections due to out of plumbness, partial yielding due to residual stresses in your members, and geometric nonlinearity and P-delta effects. And ultimately what this gives you is increased accuracy from your steel design.